Good night, everybody. I think this problem was proposed back in 2006. I'm sure it's been solved a million times, but it's new to me. Now, my very first approach on this problem, which involves just an arbitrary triangle, was to use the standard, I think they call it the Ravi substitution or something, Ravi substitution, where any one side has to be less than the sum of the lengths of the other two sides. All right, that's called the Ravi substitution, I think. And I tried that, didn't have any luck. So I went with the Law of Cosines. Now, the typical assignments here, we'll call this side A if you want to. Even if you don't want to, we'll call this B. We'll call this C. And then we'll go ahead and, a lot of times they'll use uppercase letters right here, I think, in this position, but I'm just going to call it theta. So here's a formulation of the Law of Cosines. And it's easy to remember because if theta is pi over 2, the cosine of pi over 2 is 0, and you just get the well-known Pythagorean theorem for theta is equal to pi over 2. Now, so this is what we get with these assignments for the sides. Now, right here, this piece right here already, you go, how did we get here? Well, notice that we have this condition here, a squared plus b squared is equal to kc squared. So they're equal to each other, so you can divide equals and equal equalities and get another equality. So if you divide this part right here by kc squared, okay, which is the right-hand side of this, right? And divide this whole object by a squared plus b squared. Right, that's how this happened. That answers this y question. Okay, so we're doing pretty good because we're trying to show that k is equal to 1/2. We're already in a form here where if we can get something going here, we can just take the reciprocal and start sailing, right? Now, so anyway, the y here is answered by this question. Just dividing through like this, you end up with this, okay? Let's move along. Now, something called the AM-GM inequality gets rid of this piece right here, and that should be fairly recognizable. AM-GM inequality goes like this for this particular case. It would be stated as a squared plus b squared. It says the arithmetic mean is always greater than or equal to the geometric mean. Equality, of course, occurs when the values are equal. So this is equal to, or greater than or equal to, the square root of the product. So it's a fundamental inequality in the sense it relates addition and multiplication. Okay, like that. But notice this part, of course, is just equal to AB, right? And so you can see pretty quickly how this happens, right? What you get right here, if you multiply by 2 and divide, you would get 1 is greater than or equal to, okay, multiply by 2 and you get 2AB, right? And then, of course, divide by the sum a squared plus b squared. Okay, so we have another inequality. This all holds because the AM-GM holds for positive values, and we're talking about positive values at the sides of a triangle. Okay, but you can certainly see how this truth that follows from the AM-GM inequality is what makes this piece go away. Okay. And we get a less than or equal to condition by just removing the 2ab, a squared plus b squared, which we know to be less than 1, right? So that's the answer to this y question. Now, of course, if you reciprocate an inequality, you reverse that sense of the inequality. Well, okay, let's just do that right now. Let's just write it down. So we know that k must be greater than or equal to 1 over 1 minus cosine theta. And really you could remove the inequality right here. Unless theta is equal to pi, you know, it's not, which would be a straight line. This is just going to be strictly greater. But I'll go ahead and write cosine theta right here. So we know that k has to be greater than this expression. All right. Now, so we can assume that we're living in the interval, I guess, 0 to pi over 2, or no, 0 to pi, right? Because pi could be theoretically a straight line, right? Which is, I guess, some kind of degenerate triangle. But we can apply the quotient rule of calculus right here. In other words, if we do dd theta, let's go, if we go d theta of this thing, 1 over 1 minus cosine theta. Now I won't go through all the steps of the quotient rule, but what happens is that you end up getting the derivative. Let me just write it down. The derivative of cosine is minus sign. There's already a minus sign here, but then there's a minus again because of the way the quotient rule works out. So you end up with minus sine theta. Over 1 minus cosine theta quantity squared. Okay. In general, it'd be minus f prime of x over the object itself squared. Okay. Now, one thing to notice here is that, and this lines up with what you would think, when cosine of this, if you set this equal to 0, you certainly get theta is equal to pi. And if that's something you could kind of see by inspection without even doing this probably, even though people may not believe you, the cosine of pi is equal to -1, right? And so you get 1 minus a -1 right here, which would be 1/2. Okay. And so that, just knowing what's going on with the unit circle, you would see it could never be any smaller than that. But if you really want to take this a step further, the first derivative test, if you pick theta slightly less than pi, okay, slightly less than pi, well, the sign of any from between 0 and pi, for example, the sign is positive, right? So you see, you would get, and this is an abomination of notation here, but you would get dd theta. Hopefully you guys will tolerate that, but dd theta would be less than 0. This is what they call the first derivative test, right? See, because that would make this positive if you're to the left. Just think of the graph of sine theta. It's positive from 0 to pi, right? So that would make dd theta negative. That means the tangent line would be leaning to the left of the critical point pi, you know? And then in a similar fashion, if theta is greater than pi, but less than 2 pi, and I'll just write greater than pi. This is not perfect, but you get dd theta is positive, okay? So that's what they call the first derivative test. You could try the second derivative test. I think it's a little harder to find the derivative in this case, but you get greater than 0, okay? So that implies that this is going to be a minimum value down here, right? I mean, that implies that theta equals pi leads to a minimum value, which proves that k would be greater than 1/2, right? Because again, if theta is equal to pi, this is equal to 1 over 1 minus a minus 1, right? Cosine of pi is -1, so that would be equal to 1/2. See, that would be a minimum. This first derivative test of it being 0 to the left of pi and being less than 0 to the left of pi and being greater than 0 to the right of pi indicates that's a minimum value, but that's what we're looking for because it's that means that k would be greater than or equal to that minimum value. That's the minimum value of the function, okay? And so of this function right here, okay, which is what this ended up being, you know, after just a little bit of manipulation, okay? So what we get right here is that we've proved it. We've proved that k is greater than 1/2. Since 1/2 is the minimum value, and really technically can never achieve theta is equal to pi, because that would just be a dried up triangle. That would be a straight line. If theta is equal to pi, this is just a straight line, right? Not a triangle. So we can without any, you know, we proved it from right here. I hope that's convincing to you guys. All right. So anyway, I'll put QED here. I left out some commentary, but hopefully it's convincing. Okay, thanks for reading.